Alright, let's change gears a little bit and actually dive into a topic your book covers in Chapter 4, molarity. I think it makes more sense to at least introduce it here in Chapter 3. Besides, as you'll see before too long, there's already an absolute heck ton of stuff in Chapter 4 anyway. So far in this chapter, we've analyzed chemical reactions purely by doing stoichiometry in terms of given masses of compounds in grams. But, as I've stated previously, a lot of chemical reactions take place with the reactants and products dissolved in water, or in aqueous solution. If you were analyzing one of these reactions, how could you easily determine the masses, say, of the reactants if there's also a bunch of water involved? For this reason, we have ways of expressing how much of a given compound is dissolved in a certain volume of liquid, molarity. Specifically, a homogeneous mixture, especially one with a major liquid component, is called a solution. And the molarity of a solution tells you, if you measure 1 liter of that solution, how many moles of a solute, or dissolved compound, would be present. The major component of the solution, which is water if the solution is aqueous, is termed the solvent. If you want to make a solution with a certain molarity in a lab setting, here's one main way of doing it. Measure out the appropriate mass based on a certain number of moles of the solute and add it to a volumetric flask of the appropriate volume. The volumetric flask in this example is 250 milliliters, so it would be used to prepare 250 milliliters of our solution. Next, you add enough solvent to dissolve the solute. Once it's all dissolved, you continue adding solvent until the liquid level reaches the calibration mark on the flask, at which point you cap the top of the flask and shake it to mix the solution together. Since the molarity of a solution corresponds to the number of moles of solute dissolved per 1 liter of solution, and is an intensive property, the formula for molarity is the number of moles of solute in a given amount of solution divided by the volume of that solution expressed in liters. So for something conceptually simple, if you take 1.00 moles of sodium chloride, which is about 58.4 grams, and dissolve it in enough water to make 1.00 liters of solution, you'd have a 1.00 molar solution, molar being the unit of molarity represented by a capital M. Note also that it's not 1 liter of water, but rather the amount of water required to reach 1 liter volume in total. This can't be precisely determined ahead of time. You just keep adding water to the volumetric flask until you reach the calibration mark. If we look at something a bit more complex, in other words, not just 1 divided by 1, how could we make 1.5 liters of 0.250 molar glucose? Glucose is C6H12O6, which if you add it up has a molar mass of 180.0 grams per mole. Just like we can't use molar mass as a conversion factor between grams of a pure substance and moles, we can use molarity as a conversion factor between liters of a solution and moles. So if we take our target volume, 1.50 liters, and multiply by the molarity, a ratio of 0.250 moles of glucose to 1 liter of solution, we get a total of 0.375 moles of glucose. We can then use the molar mass to figure out what mass of glucose that is, 67.5 grams. One way to make a solution with a given molarity is what we've seen so far, weighing out a solute directly, adding that to a flask, and adding the appropriate amount of solvent. Another way is to start with a solution with a higher molarity and add some more of the solvent, resulting in a solution with a lower molarity. The higher molarity solution is said to be concentrated, and the resulting lower molarity solution is said to be dilute. The process itself is called dilution. The operating principle here is that when we measure out a certain volume of the concentrated solution, we know how many moles of the solute are present based on its molarity and volume. If we then add more pure solvent, we have the same amount of moles of solute that we started with, but now dispersed throughout a larger volume. The equation for this is that the initial molarity and volume used of the concentrated solution, multiplied together, will equal the resulting molarity and volume of the dilute solution produced. One nice thing about this equation is since volume appears on both sides of the equation, you don't even need to convert your volumes to liters first, because if you have milliliters on both sides, those units will just cancel each other. Here's what the process actually looks like. We use a graduated or volumetric pipette to transfer a measured volume of a concentrated solution to a volumetric flask, and then add solvent with mixing until we reach the calibration mark. Let's look at our dilution formula in action. As the lab manager, whenever I buy sulfuric acid from a chemical company and it gets shipped to UNG, it arrives in bottles with a concentration of 18.0 molar, or moles per liter. If I wanted to use the stock solution to make 250.0 milliliters of a sulfuric acid solution with a concentration of 0.500 molar, how much of the stock sulfuric acid would I have to use? We know the starting molarity, 18.0, and the target final molarity, 0.500. And we also know that we want to end up with 250.0 milliliters at the end, so we're solving for the initial volume in the equation. Plugging in the numbers and solving for initial volume, we get 6.94 milliliters. So to make this solution, I'd need to add 6.94 milliliters of the 18.0 molar sulfuric acid to a 250 milliliter volumetric flask, then add enough water to reach the calibration mark. And we end up with our desired concentration, 0.500 molar. Molarity comes into play when we're dealing with the stoichiometry of reactions in aqueous or other solutions. Like with previous examples, we use stoichiometry and a balanced chemical equation to figure out, given a certain amount of one reactant, both how much of another reactant is required to react with it, as well as how much of the products can be produced. What's different with solution stoichiometry, though, is the way we determine the number of moles of our first reactant isn't the mass divided by the molar mass, but the volume of the solution multiplied by the molarity. Let's see a concrete example. Let's say we have 50.0 milliliters of a 0.100 molar sodium hydroxide solution. We want to react that with a sulfuric acid solution with a concentration of 0.250 molar. What amount of that sulfuric acid solution do we need? The balanced equation for the reaction is provided here. We know how much sodium hydroxide solution we have and what its concentration is. That means we can determine how many moles of NaOH we have, which using the balanced equation we can convert into the corresponding number of moles of sulfuric acid needed. From there, we can use the known molarity of sulfuric acid as a conversion factor to find what volume of that solution will be needed. So we start by multiplying the volume and molarity of sodium hydroxide. To make the units cancel correctly, we need a conversion factor between liters and milliliters, since the volume portion of any molarity conversion factor is 1 liter. That gives us 0.00500 moles of NaOH. We then convert that using the balanced equation coefficients into moles of sulfuric acid and multiplying the resulting number of moles by the molarity, but inverted so that the units cancel, gives us the volume of sulfuric acid needed, although we'll probably want to convert that into milliliters to make the result more convenient. And we get 10.0 milliliters of our sulfuric acid solution needed to react with the given sodium hydroxide solution. Okay, the math got kind of real in this chapter. Hopefully you'll be able to follow up by working on the homework to ground yourself in these types of problems, and if there was ever anything that didn't make sense, you can always go back and re-watch that portion of the video. And of course, you can reach me during virtual office hours, or talk to me in class or outside of it via email. I want to wrap up with a reminder that attendance is never an absolute requirement in this class, although I do intend to make the most of our limited face-to-face class time. If you're ever worried about your own safety, the safety of people you're close to, or the safety of your classmates on the basis of this pandemic, please stay home. I'm happy to work with anyone that's quarantined, either by choice or necessity, to make sure you stay caught up. Chemistry is important, but your personal safety, as well as that of your family, friends, and the community, will always be a priority for me. Stay safe out there, everyone.